And welcome. It's wonderful to see so many people here. So, my name is Nick McPhee. This is a kind of experimental, probably 1 year project of live streaming software development, which I'm calling Unhindered by Coding. I started back in late May. And over the summer, I was just doing Tuesday mornings and Saturday mornings, my time here in Minnesota. And now that summer is ending and like classes start here at the University of Minnesota Morris tomorrow. Oh, today, actually. Classes started today. I hope things went okay if anybody is in that community. And so I'm on sabbatical this year, not teaching classes. And one of the things that I'm doing on sabbatical is learning some new programming languages and libraries and working on a variety of projects. And one of the things I wanted to experiment with was actually programming live as a way to sort of structure my programming work and also hopefully interact with people. And the work over the summer has been great. I've had a lot of good people sharing good ideas, helping me learn things, correcting mistakes I've made as I'm learning new languages, and also just, the silly stuff that you do when you're programming. So it's kind of like pair programming, but on steroids when it's going well. And that's pretty nifty. So I'm going to experiment with adding 2 other sessions. So I'll continue to do the Tuesday and Saturday mornings where I'm actually working on building a web app using Rust and a library called U. Rust can compile to WebAssembly, so you can build web apps in Rust without any JavaScript involved. And U is a React-like library for Rust. I don't know React, so I'm kind of learning Rust and U and React halfway, because you're kind of learning U is a bit of learning React. So I'm learning a bunch of new stuff in that. And there's a fair bit of kind of web development complication that comes up in that project. I've also kind of on the side been working on some research related stuff. And I have some course labs that need to be updated or just written from scratch. I want to bring Rust into our systems lab course in a more serious way. I added a few kind of on the fly, done quick, not very substantial Rust labs a few years ago, but I'd like to do something more and more thoughtful. And so that's a sabbatical thing I'd like to work on. So I've added two additional streaming episodes a week to try to address those other things. So I'll continue to do the Tuesday and the Saturday, and those will be focused on the web development project. But I'll also be doing Wednesday night, which is what we're all here for right now, from 7 to 9. And I'm going to be, I think, working on Evolutionary Computation project on Wednesdays, which I'll explain more of a little bit. And then Saturday afternoon from 2 to 4, which I think will be working on the lab projects. So that's more history than you cared about. So let's say a little bit about evolutionary computation and what I'm actually going to be working on today. Definitely ask questions if you don't know Rust at all. You don't know anything about evolutionary computation. You just don't know what the hell I'm doing at any given moment. Absolutely ask questions. So evolutionary computation, super short version. You have some problem that you're trying to solve. You don't know how to solve it, but you know how to recognize a solution when you see one. And in particular, you've got some kind of gradated scale that you can grade solutions on. You can say, this is pretty close. This is nowhere close. This is kind of in the middle, right? You've got some scale you can use to sort of measure, are we headed in the right direction? And then evolutionary computation approaches this by saying, let's create a bunch of random solutions, and we'll see examples of all this in code in a second, but let's create a bunch of random solutions and then score them. And most will be terrible because they're random, right? I mean, they're not going to be any good at our problem, but hopefully some will be less terrible than others. We take the less terrible ones out, we mutate them, so modify them in small ways. We maybe take two and merge them together in some fashion to make a new one. But in some way, we make a bunch of new ones. Again, most of those are going to stink, but hopefully some will stink less than others. We take the less stinky ones, use them to make a new population, and you go until you get something you like, you run out of time, you run out of computing resources, whatever. No guarantee that it works, but it actually historically, demonstrably does work in a lot of interesting ways. And people have used tools like this to evolve satellite antennas and solve 3D printing of rocket engines and all kinds of things. I mean, this has been used for all sorts of stuff. A particular area of evolutionary computation that I have done a lot of work in, primarily so evolutionary computation has been my primary research area for close to 30 years. And the particular subset of evolutionary computation that I've probably done the most work in has been an area called genetic programming, where the thing you're evolving is actually a computer program. And we won't get there today, but that's sort of one of the directions I'm headed. So, as I said, I've done this kind of stuff for a long time. I've written evolutionary computation systems in a number of different languages, including like Lisp and Java, Python. More recently, like the last 8 years or so, most of the work that I've done has been in Clojure, which is a Lisp-like language built on top of the JVM. And Clojure's been great for that, but it's not blindingly fast. And doing these genetic programming runs, running these programs, so we're evolving programs, we got a population of maybe 1,000 programs, and each one's being run on a whole bunch of test cases, think like unit tests in software development. And we're running these programs on potentially thousands, probably hundreds, not thousands, but potentially thousands of programs being run on hundreds of test cases. And running a program on the test case involves actually running the program, interpreting this evolved program on a set of inputs to see how it does. All of which is super time consuming. And I think Clojure is not helping us in terms of allowing us to do these runs quickly. And I think it's been a good language for getting stuff up and running fast, but the actual running of the experiments has not been fast. And that has become a pain point for me. And I think a significant part of the issue is memory management. That's a speculation, but I think that based on some data, it's not purely a guess. But I think that these runs that we're doing take up a lot of memory. And because it's mostly heap-based memory allocation, I think it's probably, or at least there's a lot of heap-based memory allocation, I think there's a lot of thrashing and stuff that goes on that isn't helping us. And so as I've been teaching myself Rust, I was thinking, well, I wonder how much faster Rust would be than Clojure doing the same thing. In theory, I would expect it to be somewhat faster because Rust is compiled sort of to the bare metal, and Clojure is sort of converted into JVM code, which is then maybe compiled by the just-in-time compiler, and then run on there's a lot of layers there, and these are not zero cost abstractions in the way that the Rust people talk about zero cost abstractions. And there's the garbage collection, and there's all this other stuff. So I was like, I wonder, and if it's like, oh, Rust is a little faster, then fine, stick to Clojure. But if Rust is a lot faster, by maybe a factor of 10, right, that would be pretty cool. That means we could run a set of experiments 10 times as fast in Rust as we can do them in Clojure. And that would definitely open up the doors for doing more kinds of experiments. And that would be pretty nifty. So I'm kind of exploring that. I started this work on and off probably a month and a half. And so what we'll do today includes sort of getting everybody caught up on where we are. And I'm basically building out two simple genetic algorithm systems. So where the thing you're evolving isn't a computer program, but is just a fixed length vector of bits. So that's one of the simplest evolutionary algorithms. And I want to start with that to get a sense of what the space looks like and what the performance looks like. If Rust isn't better there, then there's probably not much point in pursuing the matter. But if Rust is better there, then okay, that's great. So I've been working on a Rust and a Clojure version of these, benchmarking them both and comparing results. And without getting too deep in the weeds at the moment, we'll have to maybe in a future episode actually sort of focus on the benchmarking and look at some of the results. But at the moment, the Rust is a lot faster. I mean, we're talking at least 2 orders of magnitude faster. We're not working on sort of a very interesting problem yet. But I think if anything, having an interesting problem, whatever that means, may improve Rust's advantage, not make it weaker. So I am very impressed so far. So the plan for today, in the next hour and 45 minutes, is to briefly go over the code that exists. And then I want to work on parameterizing recombination and selection in the Rust code. So at the moment I've parameterized parts of the process, but then I kind of hacked in when I realized I was pretty close to having a working genetic algorithm system. I was like kind of banged through making that work, and I need to kind of back up, migrate some of that into the more general part of the code. We'll explain that more in a second. But part of that is I'm going to have to parameterize things. I've hard-coded algorithms for recombination, generating new individuals out of existing individuals. And I've hard-coded algorithms for selecting who gets to be a parent. Those are sort of cooked in at the moment, and I want to extract those out as functions that we can pass in as arguments. And I think one of the things that's been interesting is seeing how that kind of work happens in Rust. I'm very used to that in Clojure, where functions are first-class objects. You just pass them around willy-nilly. It's easy. It's great. It's not type-checked at all. So there's a lot of potential for runtime errors because the thing you passed in doesn't really do what you meant for it to do. And then in a language like Java, especially before there were lambdas, you had to create classes that encapsulated that logic because you couldn't just pass a function around. You can now pass functions around, and you do have types in Java, so that makes it a little less icky. But there's all the ceremony in Java, and I've written a lot of Java code, and I'm not super excited going back there. And also, since Clojure is sitting on top of the JVM, I guess if I cared, I could identify where the performance pain points are and write them in Java and then call them from Clojure. But I'm not convinced I'd see a huge improvement in performance. I mean, that might be an interesting exercise. Maybe we'll write a simple GA in Java just to sort of throw into the timing comparison pot. But I'm not doing that tonight. But Rust, with its really aggressive type system, it's been interesting learning how to pass functions around and what that looks like. And it's worked. I mean, it's worked well, but it has taken some doing, and I've had to think about things. And in at least one case, I had to throw up a white flag and post a question on the Rust users forum, which actually people got back to me almost immediately and explained what I needed to be doing. And I was able to kind of figure out what was happening there. So they were great, but that part's not trivial. It's easier to write this kind of code in Clojure, no question about it. But if it's 100 times faster in Rust, it's a price that may well be worth paying. So let's have a look at the code. Are there questions about anything before we actually open up the code and have a look, see where we are? Okay. Then let's find the code. There's the code. Okay, so actually, let me back out to here. We're not going to go over all of this. I'll explain things as they are necessary for the what we're trying to understand at the moment. But I want to give you a sense of what things look like. I've defined a type, alias, bit string. Sorry about the scrolling there. Which is just another name for a vector of Booleans. So in Rust, vec is a built-in type for a collection of values whose length can grow and shrink. So you can have an empty vector, you can add things to it. So this is just saying we have a vector of Booleans, and a type alias really is just another name. In fact, when you're looking at things like error messages, this gets replaced by vec bool everywhere by the compiler. You don't ever see bit string in compiler error messages. You always just see this. But it does make the code easier to read, in my experience. So that's our sort of our structure of our solutions, our potential solutions. And we can start actually as a fitness function, a very simple, like profoundly simple problem that people in the field frequently use just as a, like, does it work test case, is called the max one, or the one max problem. And essentially, if you think of this vector of Booleans as a vector of zeros and ones, your goal is to maximize the number of ones. So if your bit string is, say, 128 bits, the perfect individual is 128 ones. And it's a nice problem because you can easily compute a score for it, which is how many ones do you have? And if you have 120 ones, that's better than having 10 ones. And having 72 ones is somewhere in between, right? So there's an easy scoring function that leads you in the right direction. So in theory, this shouldn't be a terribly hard problem. And you don't need evolutionary computation to do this. Obviously, if you know that you're just doing, one max, you just return a bit string that's all ones. But if the pattern that you're shooting for is more complex, and again, you have some way of recognizing whether you're close to the pattern, this might still be a reasonable approach. So count ones is our scoring function, or is one of the scoring functions that I've implemented, and it takes an array of a reference to an array of bits. Now, so there's a few things that are important here and are about to come up in a big way when we go to the individual .rs file. So a vector of things has an unknown length. It could be 0, it could be 1,000,000,002. We're just saying we have a vector of things. And you could ask a vector, how long are you? And you could add things to a vector if the vector is mutable. An array, which is indicated with the square brackets, is a fixed length thing. It cannot be made bigger or smaller. And in fact, it's usually referred to here with the ampersand in front of it. This is usually referred to as a slice. So this is a contiguous block of memory containing whatever type you specified there. But that block you can't make bigger or smaller. You can possibly change its contents, but its size, the amount of memory that it takes up and where that memory is, that is fixed. And you don't have the ability to mess with that. In fact, and the ampersand here means that this is a reference to a piece of memory that contains a sequence of Booleans. So it's, if you want to think about it as a pointer, you could think about it as a pointer into memory, and at the other end of that pointer is some block of Booleans, which you can look at. You can ask how big it is, you can ask how many Booleans there are, but you can't grow it or shrink it. You might be able to modify the contents if you have mutability specified somewhere. If this does not specify mutability anywhere, and in Rust, everything is immutable unless you say it's mutable. So this is a pretty significant distinction between Rust and almost every other language. In most languages, things are mutable unless you say different. In Rust, everything is immutable unless you say it's mutable. And so this is saying we have an immutable pointer into memory where there's a block of Booleans which we cannot grow or shrink, nor can we change. We can read them, but we have no ability to modify any of it, which is fine because we don't need to modify it. And that is, so that's the name of the argument. That's the type of the argument. It's going to return a 64-bit integer, an I-64. For this problem, we could have actually returned like a U64, an unsigned integer, 0 up to 2 to the 64 minus 1. But I specified the score in individual to be an I-64 because we might want negative scores for some other problems. This problem, there won't ever be negative scores, but that doesn't guarantee that that's true everywhere. And so this returns an I-64 to be type compatible with the individual. I guess I could have made this a U64 and then done a mapping somewhere, but that would have been a hassle, and I don't really care about the extra bit, so I'm happy making it just an I mean, 64-bit integers are huge, and I'm not doing vectors that are anywhere close to that long, so we're good. So this counts the ones by iterating. So this creates an iterator over the slice, and an iterator lets us basically loop over things. And then I use filter. This is the syntax for a closure, a function, an anonymous function in Rust. So between the vertical bars are the arguments. In this case, there could be 0, there could be 7, depends on what the function is. In this case, there's one argument that is a reference to a bit. A reference to a Boolean. And that's because this is a reference to an array of Booleans, and when for an array of Booleans to talk about a particular element in that, you get a reference to it. So we end up with two references. One, because we're talking about the contents of this array, and the other coming from this guy here. So we get a reference to a bit. It turns out it kind of automatically dereferences that when we need to. So the fact that that's a Boolean, this filter needs this to be a Boolean, and it sorts out the dereferencing so that this ends up being a Boolean. So this is basically filtering the subset of bits generated by this iterator that are true. So if the bit's true, we keep it, filter keeps it, and if the bit's false, filter gets rid of it. So after filter, we have an iterator. So filter returns an iterator. So filter is a kind of iterator. So filter returns an iterator, which is going to iterate over the true bits, and then count takes an iterator and returns the number of things in that iterator. And so we're going to return that as an I-64. Count returns a usize, and so we want to map that to an I-64 here, since that's what we're expecting here. So this basically just counts the ones in a thing, and that's bits of the syntax that are relevant, and we'll see lots more of this later. I should point out, because if you've never written Rust in VS Code, it may not be obvious. This bit of text here isn't actually in the code. That's being included in VS Code because the Rust analyzer, mentioned down here, is able to infer the type. I could specify a type here, but the Rust analyzer in many cases can infer types, and VS Code, well, the compiler can infer types. And VS Code's Rust analyzer uses the same algorithms to do type inference, and it actually will include them in this sort of gray color if I haven't specified them. So like right down here, this half-len is inferred to be of type usize because bits.len is of type usize, and we divide by 2, and so this is going to be usize. So it inferred that. I didn't actually put, I could put colon usize here, but I didn't, and it inferred it, but it's showing me what it inferred, which is actually really useful because the type system can be complicated, and having the Rust analyzer and VS Code show you what it thinks things are can be super, super useful at times. Okay, so we've got, this is all I'm going to talk about in this file at the moment. We've got our bit string type. Oh, actually, I'll mention, it turns out, and the details of this get a little weedy, but it may be relevant, and it's likely versions of this are going to come up. You can pass a vec bool as a slice of an array of booleans. If you pass one of these as an argument, Rust is smart enough to realize it, and it's not, I should be a little careful here, it's not really that Rust is smart. People have implemented the conversion, and we may see examples of this kind of conversion downstream, but people have implemented conversions to go from a vector of things to a slice of things. And essentially all that's happening here is this vector has an array, under the covers in its implementation, it has an array of the things. This would be like an array list type in Java. And so if you pass a vector of booleans in where a slice of booleans was expected, it does the conversion and passes in basically a pointer to the beginning of the internal array of booleans inside this vec. But unlike Java, where if you were to do something like that, you would run the risk of allowing people to go through that pointer and destroy the contents of the array list. Here, because of the mutability constraints, I have read-only access to that data, and there is no way I can change it. So I can safely pass the pointer to this data here. I can convert the vector to a slice, a pointer basically, without any risk. I know that the person I'm handing this to cannot blow things up. And that is totally not true in Java or C or a lot of things. In particular, if you pass an array, in C or C++ or Java, people can go in and really make a hash of that array, and you don't have any control over that. Whereas in Rust, you can totally say, I'm passing this array, but you don't have the ability to change anything. You can look at it all you want, but you can't touch it. If you want them to be able to change it, there are ways to make that happen, but by default, that will not be feasible. And that's actually really very cool. So, okay, so that's all I'm going to say about that. Questions about the bit string stuff that we talked about? Okay, so I've got an individual here. And so I want to talk about that a little bit. Let's actually go up here. So in Rust, we have structures. And a struct is, well, if you come from the C world, it's like a struct, sort of. But it can do a lot of things that a C struct can't do. If you come from an object-oriented universe, it's kind of like an object minus all the functions. But there's a way to add functions, sort of, to a struct. It's not really quite the same as objects, but it is close enough that the connections are not irrelevant. And I'd be happy to answer questions as best as I understand things about the difference. But we've got a struct, individual, and this is adding a generic type. So this is similar to a number of other languages like Java, where we specify a generic type. So this is an individual generic over some type T, and it has two fields. It's got a genome field of type T. So I've tried to make this as general as possible. In what we're looking at today, this will always be a bit string, but later on, I'm hoping this will be other things like programs. And it has a fitness field, which is an I-64, like we talked about. Now, the pub parts here, again, if I don't say things are public, they are private. If I don't have a pub here, no other file, essentially, module, is going to have access to this individual type. Well, that's not good. I put it here because I want to use it, so I have to say it's pub. I made both of the fields pub, which means that at the moment, anybody who has an individual can reach in there and, oh no, actually they can't change it because they're not mute. So anybody can reach in and look at them, but nobody can mutate them because I didn't say that they were mutable. So this actually gives you a lot of the safety of private variables in an object-oriented language without all the ceremonies of getters and setters. The ability to say, here's the stuff, but you can't change it, makes a lot of things actually a lot simpler. You can still make things private if there's an implementation reason to hide some implementation details. But if you don't want to, you don't have to. So this has got a genome of type T and a fitness of type I-64. Now, impl, let's see, ignore all the, can I do that? Oh, I can. Okay, great. Thank you, VS Code. Ignore that enormous comment for a second. If you were in the middle of reading it, I apologize, because I probably just did a bad thing. We'll come back to it. And ignore for the moment the R business. We're going to have to talk about that. That's a little complicated. You can implement certain functions on structs. And that has, essentially, you're associating a function with a particular type. And these become things kind of like methods in object-oriented languages, not the same as methods in some ways, partly because there's no inheritance in Rust, but they're similar-ish to methods in object-oriented languages. And so this syntax, we're saying we're going to implement, so impl, we're implementing some feature for some struct. And impl can take a generic. So if there's a generic that applies to the whole impl, then that's specified here. So we're saying impl over some type t, individual of type t, and we're going to define a function new, and again ignore the r, that takes some stuff, and ignore the where, and returns a new individual. That's all this does. This is basically a constructor for the individual type. And so we're getting the genome here. We'll talk about how we make that in a second. And we're getting the fitness here, which really, I should call that score. I think score is better than fitness. Fitness comes with a lot of baggage, and it's widely used in evolutionary computation. But as I've been talking here, I actually think I think score is a better word. So I'm going to go with score. And then I also probably want to change that to be compute score. Okay. So we're going to make a genome, we're going to compute its score, and we're going to then construct an, imagine this said individual. Actually, if I say individual here, it'll still compile. And we can talk about why it said self in a second. But this is the syntax for constructing a struct, name of the struct, curly braces, and then the fields. And if the field name matches a local name that you're using, so normally you would say the name of the field, colon, the value you want that field to have. If the name of the field and the value happen to be the same, then you can skip the colon part and just provide the name. So actually this tells me that I probably wanted to change this as well. We need symbol to score. And notice that VS Code was smart enough when I renamed that to go from fitness colon score, no, score colon fitness to just score. That's really cool, actually. I didn't even know that it did that. So how are we constructing individuals? And if this seems a little tedious to go over all this, this gets us to where I want to, the work I want to do tonight is about this kind of function passing that's happening here with make genome and compute score. And so it's worth, for me, if nothing else, going through this just to get my head straight on what's going on so that we can talk about how to parameterize some additional functionality. So I wanted this constructor, this new, that makes, and so new, ignoring the R again, takes some arguments, we'll talk about them, and returns, and again, this could be replaced by just individual. Individual T. Oops. Do I have to do that? Yes. Okay. And so this is taking some stuff and returning an individual. And so what's all this stuff? Well, there are two things I want to parameterize on at the moment. Actually, for individual, they'll be the only two things. We won't change anything here. We'll change things in population in a bit. I want to be able to take a function that constructs a genome, constructs a new random genome, and I want to take a function that computes the score for a genome. So it takes a genome and returns a score, an I-64. I could probably give this a name, or I could, if I cared, I could parameterize on score, which I may have to do later because there are scoring systems that aren't just numeric, but the score might be a vector of values. So I might want to actually have this be a generic type and have this be like t comma s and then use s here. I'm not going to go down that road right now, but that would be a thing that might be important later. And we're going to take in a thread RNG, random number generator. So we're passing a random number generator in as an argument to new. We're sort of saying, here's a random number generator, use that one when building your initial genome with make genome and computing the score. Although compute score doesn't take the random number generator, so it's assumed to be deterministic. But we want the random genomes to be random so every time. So they're going to take this thread RNG as an argument. So we're going to pass it into new, and then new will pass it on to make genome as an argument, saying, hey, you're going to make a genome, and this is the random number generator you ought to use. And then we'll compute the score based on the genome, and then we'll construct the individual. Do I want to talk about more here, or do I want to try to move on? Do we care about the R stuff right now? At the moment, let's actually skip the R business. In the interest, because we're like 40 minutes in already and we haven't written any code. So let me hop over here to population and we'll look at what population does, and then we will look at bit string, and that'll sort of tell us what we want to change. So population is a struct that's again parameterized on type T, and it contains a vector of individuals of T. So it just has a single field. It's basically a wrapper at the moment. We might add things to it later, but at the moment it's just a wrapper around a vector of individuals with type T. And again, we have an impl population T here that has a new. So this is constructing a new population, and then this is a impl that adds a function that computes the best fitness of a population. We'll come down to this in a second, but let's actually look at this quick. Again, ignore the whole R business. New takes 3 arguments: population size, how many individuals do we want, make genome, so the thing that makes a new random genome. This is going to be what gets passed over to the individual constructor because it needed the make genome, and compute fitness will be passed as well. And we changed the name over in individual land. We should probably change the name here. Compute score. Should probably just search for fitness everywhere and see if there are places where it appears. And so here we vec with capacity creates a new vector that is allocated to have a certain size. Now you can make it bigger and smaller, but if you don't ever make it bigger or smaller, you won't pay any price from a memory management standpoint. It will be the right size, it'll allocate it the right size up front, and you'll be good. If you need to add to it, great, it'll sort of allocate additional memory as necessary and shift everything over. Again, it's not unlike an array list in Java in that regard. But if you get the capacity right, you sort of minimize your memory management hassle. So this creates an initial vector, and then we're going to extend, ignore the par part for a second, we're going to extend that vector by, so it's initially empty. This vector that we get back is an empty vector, but it is sitting on a pile of memory that's just the right size for where we're headed. instead of if we had just allocated a truly empty vector, if we'd allocated a vector, empty vector without specifying capacity, it would be sitting on basically no memory, and it would have allocated memory as it needed to. But here it allocated the memory up front for pop size elements because we knew how many we were going to want to have. So we're going to extend that empty vector, and this is going to take par extend, and ignore the par part. Extend takes an iterator that tells it the elements of the iterator are the things we're going to add to the vector. So it should be an iterator over, in our case, individual of t, and it will then put each of those individuals in the vector. And if the number that we put in is no greater than pop size, no new memory should be allocated. So this is the syntax for a range in Rust. So start ... finish. By default, inclusive on the left, exclusive on the right. Oh, makes me so happy. If you want exclusive on the right, you can put an equal sign here, and that would be 0 up to and including pop size, which would be one too many for the capacity that we provided. But 0 ... pop size will be 0 up to, but not including pop size. So if pop size was 10, we'd have 0 to 9. So this gives us basically an iterator over those values. And, well, no, sorry, it's a range, and then we turn it into an iterator. Again, ignore the par for a second. We turn it into an iterator. So this is now an iterator over these numbers. So this iterator would give us back 0, then 1, then 2, up to pop size minus 1. We can map over an iterator. So that takes a function and applies that function to every element in the iterator and gives us a new iterator of the results of those functions. So if we had 0 to 9 and we mapped square over that, we would get an iterator that gives us 0, 1, 4, 9, 16, 25, 36, etc. Map init is slightly different. It takes 2 arguments. Regular map just takes the operation, the thing we're going to do to each value in the iterator. Map init takes a first value that's an initial value that's going to be passed to the map operator as its first argument. So we can use that to initialize something that will be shared across all the rounds of the mapping, which in this case is going to be rand : thread RNG. That just gives the random number generator for the current thread. And we'll talk about why the thread's relevant there in a second. But this gives us the random number generator for this thread. And that then is going to be passed in as the first argument to the mapping operation. The second argument would be the number that came out of this range. We don't care about the number. We really just want, let's say pop size is 100. We want 100 individuals, and knowing that this is individual 13 and that's individual 27, none of that matters. So we get the number because we're iterating over a range like this, but we don't care about the number. So we could have called this like index. And now notice we get a yellow squiggle, and it says that this is an unused variable. So we never did anything with it. So it's like you didn't need a name here. And Rust is very good, as are several more recent programming languages, including Clojure actually, about allowing you to not name things that you don't need to name and be kind of explicit about the fact that you're not naming them. And so if you prefix a name with an underscore, it's a way of indicating that this is never going to be used. And in fact, you can go kind of radical on that and just use underscore as the name. And it will then sort of say, hey, this is not being used, and there's no way to use it if you wanted to. You don't really have a way to refer to this anymore. So this is saying our mapping operation is going to ignore the index, but it is going to care about the random number generator, and it's going to call individual new, and we're going to pass it make genome, compute score, and RNG. Now we probably do need to say something about these two ampersands. Yeah, I think we need to say something about those two ampersands. So when you call a function in Rust, the default behavior is that you give ownership of the value that you're passing as an argument. You give that value to the function that you're calling. It now owns it, and you don't get it back. It's gone. You have handed it away, and you do not expect to see it again or use it again. And this borrowing idea in Rust, if you're new to it, is a little confusing, but man, it's really powerful. And this is how Rust avoids whole piles of nasty memory problems that plague languages like C, without introducing a garbage collector like languages like Kotlin or Java or Clojure, Ruby, Python. Name almost any sort of other recent language that probably have a garbage collector. And Rust doesn't have one. And it manages to still produce memory safe code in part through this borrowing thing. So kind of what we're saying here, we're passing a reference to make genome and a reference to compute score. So we're saying we're going to loan you, you can borrow make genome and you can borrow compute score, but you don't own them, and when you're done, I get them back. And because we're also not making them mute, I mean, these are functions, so it wouldn't really be an issue. But if these were non-functions, the fact that we're not saying mutable anywhere means that we're letting you borrow them, but you can't write in them. It's not like library books where you could scribble in the margin. We're going to loan them to you, and they're going to come back to us exactly as we gave them to you. And we know that. Rust is going to guarantee that for us. And that is really slick. So that's where the ampersands come from. Let me say a little bit about the par thing. We could do all this without par. So I could get rid of this, and I could get rid of this, and this would still work. Or not. Actually, no. Map init is specific to par iterators. That's interesting. Okay. Now, do I wonder actually, I'm not sure if I need, not part. I'm not sure if I need both pars or if I'm overdoing it there. Because that makes a parallel iterator. Do I need? Yeah, I think I do. I think I need it in both places. Yeah, because this wants a par iterator. Yeah, okay, that's the problem. So par extend wants a par iterator, so I need wow, that did not rewrite. There we go. Okay. I need a par iterator and a par extend. Okay. I'm good. So what this is doing is actually super slick. This is, so let's say our pop size is large, say 1,000. We're going to need to generate 1,000 random bit strings, and let's say our bit strings are 128 bits long. We're going to need to make 1,000 bit strings that are 128 random bits, and we're going to need to compute the score on each of those. So we're computing 1,000 scores after generating 1,000 random bit strings. And that's going to take a little while. I mean, not a lot of a while, but some scoring functions can be very slow, actually, and could take a fair bit of time. it would be nice to take advantage of all the spiffy cores on our computer and be able to say, hey, do that in parallel in some meaningful way. And this is one of the things that's really nice in Clojure, is it's very easy to parallelize code. And because of the fact that most Clojure code is functional in the same sense that it doesn't modify data, it computes new things and returns it, it's safe to parallelize things really aggressively. And so it's pretty easy in Clojure, certainly much easier than in Java, to generate a parallel computation, a parallel version of this. Well, it turns out in Rust you can do the same thing, and it's really slick. And this is, I think, one of, if this had not been there, if the what they call it, fearless concurrency in the sort of Rust jargon, I think the fearless concurrency is one of the reasons I wanted to explore Rust, because I think concurrent programming is absolutely where we're headed, that in the future more and more code is going to need to be concurrent, and languages that like support that well are going to be more and more important. And Clojure does that really, really well, which is one of the reasons I was interested in Clojure. Elixir is great at this, and I highly recommend looking at Elixir if you're interested. But sort of the threaded aspects of Rust and the fearless concurrency, man, that stuff is really shiny, and this is a great example of it. I could just say extend and do into iter. I'd have to fiddle the map a little bit because map init apparently isn't in the regular iterator class. It's only in the parallel iterator class. But I could do this, and I would just get a sequential piece of code that would go through, and if let's say we got 1,000, population size of 1,000, would construct the first individual, add it to the vector, add it to the iterator, so it would then be added to the vector. Construct the second individual, add it to the vector. Construct the third, add it to the vector. Just sequentially do that. By saying par extend and into par iterator, both of which come from the Rayon library, which are called crates. Libraries in Java, in Rust, are called crates. The whole sort of industrial theme, Rust, crates, yada yada. The Rayon crate gives you a lot of very cool parallelism tools that work really, really nicely. And here, by saying par extend, I'm saying I want to extend this, but not sequentially, but in parallel. And I want you to figure out what that looks like, where U is the Rayon library. And so the Rayon library is actually going to like look at how many cores you have on your machine and how big the array that you're filling is, actually sort of the length of the iterator that you're processing, and it's going to decide how many threads to create and how to divvy up the work. And that's really quite slick. And very similar to the pmap operator in Clojure. But in a sort of, again, type safe, you get past this crazy compiler and all the type checking stuff. So this is really, really cool. So this does all this construction in parallel, and all the cores get used. And that's really slick. And ignore the green thing. That was just, so that's just a serial version, a non-parallel version of the same thing. So we could create a random number generator and then loop over 0 to pop size, create an individual, and push it onto the pop vector. So this would be a sort of a simple way to do it without the parallelism. But this, without being a lot more complicated, I mean, it is more complicated, but not a lot more complicated, gives us this in parallelism. In parallel, we'll use all our cores. Woof, everything's like spiffy. And then we construct a population with this as the value of the fields. And the fact that these had to be different makes me think I probably ought to just change this name, to be honest with you. If I call this individuals, then that's probably a better name, and it simplifies this. So that was good. Okay. Let's stop there. Let's go over to bitstring, and actually let's run something here soon before everybody completely loses their what little attention span we all have. Let me okay, so let's actually come down here. So this this code actually runs, let's see where, so next generation, yeah, okay. So this code basically does a simple evolutionary algorithm, and this is where I want to make changes, because there's stuff that's sort of baked in here that needs to not be baked in here. So you can impl over a generic type. So like we had impl over population T here, but you can also impl over a specific type. So this is saying we're going to add functions not to the generic population of T, but we're going to add them to the less generic, not generic at all actually, population of bit strings. So this will be a vector of bools, and these functions, everything in this impl block, which is sort of here to the end of the file, all of this only applies to population of bit strings. So we're hard coding stuff about bit strings here that ultimately may not want to be hard coded to bit strings, but also more importantly has other things hard coded into it that I don't want hard coded there. We've got a new bitstring function which will be used to construct. So when we pass in a make genome function over here in population and individual, this is going to be a function that makes a new random bit string. And so we're going to take the why do we pass in pop size? Oh, this is a bad name. So this really should be like new bitstring population. Actually, I'm going to change that since I'm changing all kinds of names here today. New bitstring population. Although I feel like Clippy may fuss about that, but okay. It's clear to me that that's making a new population of bit strings. So we're going to pass in the population size, and actually this now got long. So let's bring you out here, and then you, and then you. Boom. Oops. No. Over. So we're going to take a population size, bit length, and then a fitness scoring. Let's call you compute score, because I think that was a better name and I should be using it. So we're function that computes scores, and we're going to return. So self here is when you're in an impl, self is going to refer to the type that you're impling on. So where I use self here, that is a population of bit strings. And I can just say self. And I guess from reading things, there seems to be some disagreement about whether it would be better to say self here or population bit string. Clippy, which is the sort of linting tool for Rust, wants you to use self. But there are people that are like, well, no, maybe it's more readable if you actually are explicit about the type. I know when I was new to this, I was always trying to figure out what the hell self was. On the other hand, if you use self and I change this name, I don't have to change this or this. These will just be whatever this name is, even if I change it, which I think is one of the reasons why they're like, yeah, you should probably say self here. So I'm saying self, which is why over here we had some self instead of individual right here and right here. And those changes will make Clippy happier. So here we're saying if we want to make a bit string population, we'll pass in these things. And now we'll call the more generic new on population, which is the one that's defined over here, this new here. We're going to call that passing, and oh, actually, let me scoot you over to the right. Open, split, right. There we go. So population takes pop size, make genome, and compute score, and we're going to call it. Oops, I want to be. Where'd bitstring go? There we are. So bitstring, we're going to call it with pop size, which is coming from here. Make genome, which we're actually constructing here as a closure out of this, or we're just going to make it, and then compute score we're going to pass as an argument. And so the make genome is going to be a closure that takes the random number generator and calls make random, which is defined here, right there. So this make random constructs a random collection of bits, a vector of random booleans, with the specified length in the random number generator. So we're past this closure in as an argument, and it will make the genome, and that's awesome. Now, and that's nice and generic. Where things get a little whack is down here in next generation. Here I was writing in a hurry, and there's a lot of stuff here that's not very generic that I would like to make more generic. And that's where we're going to try to get to tonight. Even though I've spent an hour talking and not actually writing code. But it's useful for me to explain this stuff. So next generation is taking ampersand self as an argument. What the heck is that? Well, we're in an impl. Actually, we can see it better down here because VS Code sort of reminds us what we're in down at the bottom. We're in an impl of population vec bool. So if we have a function and if the first argument is ampersand self, we're saying that you can call this as p dot next generation, and where p is some population, and that p dot, the p in front of the dot, is going to get passed in here as the first argument. In this instance, the only argument, but you could have other arguments. And it's going to be of type population vec bool. So this allows us to have the kind of object-oriented this dot that, noun dot verb sort of syntax. Looks a little like Python if you've done objects in Python, but quite different from, say, Java, where this is implied and you don't ever say anything about it explicitly in the function signature. But in Rust, as part, I'm assuming, of the very explicit approach to typing, they actually have this as the first argument whenever you're writing functions that are part of an implementation for a structure. So this is going to take a reference to a population of vectors of booleans as an argument, and it's a reference, so we don't own it. We can read it, but we don't keep it when we're done, and we can't change it because there's nothing in that type that says anything about mutability. So we can see the old generation, but we cannot modify or take ownership of anything in the old generation. And so the first thing I do is I grab the individuals out of that population, And I assert that the old set of individuals is not empty. So this is a little awkward. Rust macros, I don't know if it's required or if it's just good form, but they end in exclamation mark. They end in bang. So this is a macro. And they also still use exclamation mark for logical negation. So this exclamation mark is part of this name and is saying this is a macro, and this is saying logical negation. So this is saying we're going to assert, and because of the exclamation mark, we're asserting, not really, it's just that it's a macro, that it's not true that previous individuals is empty. So we're asserting here that previous individuals is not empty. This will panic if this assertion is not true. And panicking in Rust is kind of like throwing an exception, but not quite like throwing an exception. So we are asserting. So it's not quite like throwing an exception, but it's kind of like throwing an exception. But if you panic, the code will stop cold right there. Like, boom, program's done. So if somehow the collection of individuals from the previous population was empty, the program would quit. And that's important because we're going to want to do things that only really make sense if the population is not empty. So things like selecting a parent to be selecting an individual to be a parent of a new child in the next generation only really makes sense if the population is not empty. So we're kind of saying, hey, this is really important. Let's check this. I'm just giving a name here to the number of individuals in the previous generation because it turns out I refer to that exactly once. Why do I thought I referred to that more? I think at some other point I referred to that a lot, but it doesn't look like I do anymore. I'm going to leave it alone for now. And then again, we're going to parallel iterate over this range. So we're going to make a new vector of individuals by parallel iterating over a range. And so we're going to we're going to use all of our cores to generate the new individuals in the next generation, which is cool. And actually, it's interesting looking at this. I clearly did this two different ways before. Let me reopen this to the side. Split right. So here, I started off with an empty vector and used parExtend. Whereas here, I skipped the parExtend part and then used collect at the end to turn that into a vector. And I don't have any clear reason why those are different, other than I was probably learning things and maybe looking at different sources when I did those two things. They obviously both work. And I don't know, I guess I don't know if there's a performance difference between those two. That's an interesting question. And I'm going to make a note here to myself. To do a performance test to see if there's a difference between this use of into pariter and collect and the approach taken in population.rs. Boom. So I should definitely check that. Okay. I might even do that tonight instead of what I was thinking we were doing because I've talked so much. So yeah, this just does the same thing basically. Map init, we hand it the random number generator, map op. Now in this case, I actually, and this is where things like from here to here is a hacked up mess. Just being real upfront about that, and that's what I want to clean up. Because I was just like, oh look, I can code, and I can code some more, and my hands can go flappy flappy on the keyboard, and that's always a win. So I actually use the index here in a subtle way, which will, well, not a subtle way, in a simple way, which we'll talk about in a second. If I is greater than 0, so we're going to treat the first item in the new population differently than all the others. And that's why we actually sort of capture this value here and check it in this if statement. If we're not doing the special thing, which I'll talk about in a second, then we choose a random individual from the previous population. And this implementation of choose is really simplistic. Go to definition. Oh, hey, no, that's over somewhere totally than I thought. Choose is actually built into vec. That's right. So since previous individuals is a vec of things, choose RNG is, say it's built into vec is not right. It's really in the rand library, but it's been added to vec. So I can say choose and pass it in RNG, and I'm going to get a random element of this vector. Now, the thing that's a little tricky is this returns an option of an item. So item here is the type for the things in the vector, and we would want choose to give us an item from the vector. The problem is if the vector is empty, there isn't anything. And this is one of the things that Rust does, I think, a really wonderful job of, is forcing us to be real honest about this kind of thing, as opposed to the dreaded null pointer exception problem that we would get in like a lot of other languages. In Rust, choose returns an option type, which has two variants, a sum variant that actually contains the item. It's like there was one and here it is, or a none variant that's like, this thing was empty and there wasn't anything. I could not find you a thing that was like what you asked for. And then we have to deal with that. We are forced to deal with that. And there are various ways we could deal with that. One, which is generally not optimal, but actually I think is the right answer here, is unwrap. Unwrap takes a option type, and if it's sum, then we just get the contained value, and if it's none, it will panic actually. So if choose returns a value wrapped in sum, this will just take the sum off, and we will have the selected individual. If this were to return a none value, this unwrap would panic. And that would be bad. However, we've asserted that previous individuals is not empty. And that's how choose can fail. If you read the documentation, choose probably even says that here, maybe. Yeah, none if the slice is empty. And we have asserted that it is not empty here. So we will have already panicked up here. And so I'm happy unwrapping here because this shouldn't ever happen. We could do fancier things, but I don't think they're necessary in this context. And you can ignore the commented out versions. Again, this is me hacking around. And then the second parent, we're calling self.bestIndividual. Best individual is defined here. And so this is in an impl on population bit string. Probably could be on, actually this could be totally moved to population of t, because there's nothing specific about bit strings here. I should move this to population t. Do that in a second. So best individual, again, it and and self, reference to self as the first argument, so we can call things like self.bestIndividual, and it will call this function passing this particular vector of individuals as the first argument here. And so again, we assert that this is not empty, because talking about the best individual of an empty vector doesn't make sense. Oh, and I've got this allow clippy unwrap use. There's another one of those down here. I've got lots of warnings turned on. Like, I've turned on all the possible clippy warnings because I like having lots of warnings. And so clippy's like, you shouldn't use unwrap, except when you should. And then this is me saying, I know I'm using unwrap. I mean to use unwrap. I think it's the right idea. Don't be yelling at me. Because I've got this assert, I don't think I need to worry about the unwrap. And so I take the individuals, I turn them into an iterator, and then there's this nice max by key that takes an iterator and a closure, and the closure says use this value to decide what's big, and then give me the biggest thing. So max by key gives me the largest thing where I can specify what it means to be big. So in this case, if I'm trying to just maximize the number of ones, then I can just use the score and say I want to maximize by end.score. So the closure is going to take an individual, and I'll return its score from the closure. This is going to give me then an individual. And actually, if I go, let's see, if I do this, I can stop it. I can get the types will get sort of written out by, So individuals is going to be this. This iterate. Oh, actually, I guess I could even do another one. Boom. This is going to be an iterator over those. This max by key is going to return an option wrapping a reference to an individual, and then I'm going to unwrap that, and that's going to then be an individual, and that a reference to an individual, and that's what we're going to return as our return type here. Okay. Whew. So that's our second parent. So we're choosing a random parent. We're choosing the best individual so far, and then we're merging them using 2-point crossover. So this takes two individuals, the one before the dot and the first argument being passed in, and gives me back a new individual that's a combination of the bits of the two individuals. And then mutate takes an individual and mutates at the moment just a single bit. That's also not very flexible and needs to be changed. So it does that, and then so that's how we generate almost all of our individuals. Is we take a random individual and the best from the previous population, and actually noting, if we're going to stick to best here, this is the same every time through this map, and could have been computed once up front as part of the init, actually, and not have to be recomputed over and over again. I can make that a little more efficient, but I'm not worried about it right now. So we use this process to generate all but the first individual. The first individual, we're actually taking the best individual and cloning it. So we're making a copy of the best individual from the previous generation and putting it in the first slot in the next generation. So we always keep whatever the best thing we've seen so far will always move forward. We might see something better and this will get replaced, but we'll never lose the best thing we've seen so far. And without something like this is actually a very simple form of elitism. Without this elitism, we can actually get something cool and lose it. And that's kind of a stinky thing when that happens. So there are a couple of issues with this. So one is the selection mechanism is just cooked in here. If I want to change it, I'm actually having to change this code. And a lot of this commenting is me playing with different ways of choosing parents. So really, the parent selection mechanism ought to be passed in as an argument, so that we can more easily say, oh, I want to use this parent selection approach or this parent selection approach, and not have it cooked in to next generation like this. That's not good. So that's one thing that needs to be changed here. And the other is, how do we make offspring given the parent selection? So right now I've hardwired 2-point crossover and this mutate operator, but really we'd like that to be stuff that we pass in as well. And maybe those two things really are one thing in some sense that's being passed in. Probably easier to think about it actually as one thing at the moment, which there ought to be a function that will take the population and give you back one new individual. And then you can build different versions of that, and then change the way the evolution happens by passing different versions around. So that's the thing I think I really want to try to fix right now. So after a whole lot of talking, I've made a lot of changes. Let me commit those. Let me first see if there's any other place where fitness appears. Oh, hey, look at all those fitnesses. Best fitness, right. We were just there. That's over here, I think, right? Oh no, that's best individual. Does that call best fitness? No. Weird. Does anybody actually outside of benchmarking call best fitness? Where is that defined? It's in population. Interesting. Why do I not have best individual in population? That's a great question that I don't have the good answer for. But let's change this name, because this should be rename symbol, best score, and then that's in a comment. I'm not going to worry about that because that probably should just go away. This would be compute score, rename symbol, compute score. And now there's a whole bunch of... So evolutionary computation people started using fitness way back decades ago, using the word fitness. And it turns out we mostly used it incorrectly. Like if you say fitness in the presence of a biologist, then in the way that it's used in evolutionary computation, they will have a fit. And it's a fight you don't really want to have. And so, unfortunately, I tend to use fitness a lot because I'm old and I got into this when people still use that as the primary word, and it's still widely used, but doesn't make it good. And so, I think if I make, I don't care about that. If I change fitness to score throughout, that'll actually make me happier and probably be a better choice in the long run. Okay, So I think that's all of those. Let's commit all of this nonsense, and then let's see if we can actually do some real work. So this is all about changing the names. This is all about changing the names, all about changing the names. Yeah. All about changing the names and more about changing the names. Okay. I'm gonna stage all that. So change all occurrences of, oh, I can never spell occurrence. Is it one R? No, it's E. R? Okay. Fitness to score. This changes all occurrences of fitness to score, and also changes new bit string. So I should say that's in population. Whoa, that was bad typing. To population, new bit string, population, to try to clarify the intent there. Boom. Okay. Whew. Now, let's try to actually change something. Let's run something. Everybody's been so patient. Let's actually evolve something, because that would be fun. So I've got a main here that makes a new population, and notice I declare that mute, which means it's mutable, and that means that population can be replaced with another population, which I will do right down here. And so we make a new population of size 1000 with bit length 128, and we're using HIF. We could change that to count ones, because that would be probably a little simpler. And then I also need to change that. Does next generation have somebody else has got to have, so I don't care about you anymore. Somebody else must have HIF. Next generation must say HIF somewhere. Where? There's got to be some reference somewhere here. Somewhere here we have to compute the fitness of the new Oh, it's cooked into these operators. So actually 2.xo and mutate. Yeah, that's another bad thing, is that 2.xo and mutate have this the score calculation actually baked into them right here, which is terrible. Like the fact that I'm having to go through here and change these in the code, really awful. So we got to fix that. But now I think it will do count ones. So it'll make a population, it'll assert that it's not empty, it'll get the best individual out of it and print that out so we can see what that looks like, and it'll print how many individuals there are on the population and the length of the best individual. So let's actually comment this out for a second so that we can, we'll just run this 10 generations. So, and then we go, oops, I didn't mean to do that. For 10 generations, we're going to call next generation and replace population with next population.nextGeneration. And that's only possible because we made this mute here. If we didn't, this would actually be a new variable. We'd have to put a let here, and this would be a new variable in this scope, which we could do, but we don't need to keep the old population around. So this will allow it to free up the memory of the old population after it's computed the next generation. And I'm becoming rather software noir here as the sun's gone down. Let's throw some light on the subject. And we get the best. We print some stuff out. Yada yada. So let's actually run that. Cargo run. Whoa. Oh, yep. I almost certainly have got a problem right here. So I need to say that I want to pull count ones out of the bit string module as well. Notice it's actually fussy about HIF here because I'm no longer using HIF. So it's like, you don't need to have that. I'm like, okay, fine. I don't care. Whoa, sorry about that. Go away. I don't care about that right now. So let's try running again. And yes, we get warned about that unused import. Now, the Rust is fast, the compiler is not. The compiler is doing a lot of work, and so Rust runs really quickly, but the compiler can be a little slow. So here was the initial population. Here was the best individual from the initial population. So out of 128 bits, it had 85 were true. So better than half, but not a bucket better than half. For 1,000 individuals, that's probably a reasonable expectation. So it's telling us the population size was 1,000. We had 128 bits. And then we went through and we did 10 generations. And the best score went from 85 to 93 to 94 to 95 to 96 to 99 to 99. So these are probably the same. So this would be a case of elitism preserving our best individual. So it wasn't able to make a better one, but this ensured we carried this guy across. And then 101, 102, 104, 106. And if we say time cargo run, so that took a little over a second. Probably a lot of that in this instance was just the printing. And we can crank this up to like 1,000. Let's go to 100 actually first. So this will do 100 generations. We'll see what happens. It looks like nothing was changing for a while, and that's because we got to the best possible score. We got to 128 somewhere. Where did that happen? Right here. So in generation 49, we got the best answer, and so for basically the second half of the run, it didn't look like anything changed because we were printing the same thing out and it turned out to be in the same place on the terminal. So sort of weirdly like nothing happened. So that did 100 generations in 4.5 seconds, which is pretty nice because it's actually doing a lot of computation here, right? There's 1,000 individuals times 100 generations. So we're talking 100,000 bit strings of length 128 have to be constructed and have to be scored. So that's quite a lot of stuff happening. And I think actually in some sense the performance of Rust is more impressive when the fitness the scoring is more complicated, because this goes so fast that a lot of the time is spent on the terminal I/O. I think if we dump to dev null. Yeah, so it went from 4.5 seconds to under 3 seconds. And I think that's mostly because we pulled all that I/O work out. So if we make the scoring more complicated, which that HIF thing did, so if we put that back without me explaining what HIF does right now, count once. This needs to be HIF. Oops. Yeah, right. HIF. And then in bit string we had HIF here and HIF here. So HIF's more complicated, and will be a little slower because the calculations are slower. So we were under 5 seconds before, and we're at just under 6 seconds now. If we do the null one, so this had been under 3 seconds before, and now it's 4.25. So it's clearly doing more of the work in the actual computation, and we're still getting improvements out at generation 99. The best possible is over 500 here. So yeah, so we got this 420 in generation 89. So if we ran this longer, it would actually find better scores. So we're evolving things, and that's nifty. But it would be great to not have all this stuff cooked in. Let's actually start by dealing with the fact that the fitness function is baked in, because I think that the fact that I just had to change that here, that's really annoying. I don't like that at all. So I think we want to change that. One thing I also think is, I think that I've got these things returning individual bit strings, which means I have to compute the fitness or the score. See, I'm bad. I keep saying fitness and I mean score. I have to actually compute the score in the call, because you can't construct an individual without a score. I could make it option score, but that doesn't really make a lot of sense. It doesn't make sense to talk about an individual in this context that doesn't have a score. And that'll just add some hassle. So really, in some ways, what I really want is I want this to just return the bit string, and then I want the score, the individual construction and the scoring to happen elsewhere, so that I'm not actually computing it in the mutation operator or the crossover operator or in the mutation operator. The fact that this appears in all three of these is not great. And I could pass that as an argument here, but I don't want to do that. I don't think that's the right answer. I think these should just not have this. And so I think these guys really should have these should return bit string instead of individual bit string, which means they're not going to be in an impl for individual bit string, because they're not going to take individual bit string as a first argument anymore. Oh, unless, maybe we keep these and they call a function. Yeah, actually, okay. I'm going to keep these here because I want to still be able to say things like 2-point crossover other parent, and then pass in the scoring function is another argument. But then what I'll do up here, where am I? Yeah, up here, I will call out to something. Is that what I want to do? So let's think a little bit. Next generation, it's gonna need to know what the scoring function is. Right now, that is hard-coded in all over the place, and that's bad. So we want this to be parameterized on that scoring function. So the simple solution would be to pass in a function here that we then use as the scoring function. One thing I'm wondering is whether it would make more sense. A population is currently just a vector of individuals. We could store the population or the scoring function in the population object, and next generation would then have access to it from previous generation and could include it in next generation. Is that a thing I want to do? I think at, oh my goodness grief, it's 8:45. I didn't realize it was so late. I think I'm not going to do that right now. Let's see if in 15 minutes we can just pass these things around as functions. So I'm going to need next generation to take a scoring function. And I really probably ought to probably makes sense to create a type for this, a name for this, because I'm going to use this now. I've already used it in several places. I'm going to use it in some more. So this is the type for compute score. And to explain this fully, we'd have to get into this R business. For the moment, you can just think of this as a slice of Booleans, an little array of Booleans. And the send and the sync are necessary because of the threading. Since I'm using the Rayon libraries, we have to say that this compute score thing can be sent to other threads and will behave well when it gets there. And that's really what send and sync do for me. So if I come back here and I say I want self and that, then I can, for the moment, let's just pass. Do I really want to do that? Yeah, I mean, because we're just about out of time. I don't want to. Oh, and I need to copy this whole R business. So I need R. And I need the where business. So boom, 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 boom. Which I'm not explaining because we want to get somewhere here. Oh, I don't need. Oh, this would be T. T? 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 Oh, foo. Am I going to get into a problem here that I am not prepared to deal with right now? Okay. So do I just need T and R? Okay, no? Yeah. Yes, okay, that's good. And then the error that I'm seeing is because I'm not passing a compute score over here in main. So I'll do that. So I'm going to be bad for now because we're just about out of time. I'll fix this later. We're going to pass in compute score here, and we'll pass in compute score here, and that's all terrible, but we will fix it later. Boom. Yeah, okay. So let's fix the problems up here. So this needs to take compute score. Let's find its type again. I really have got to give a name to that because that is terrible. Oops. Catch the C. Boom. Boom. And we're going to have to do, again, T. No. I don't need T here. Did I need T down here? Actually, no. Since this is all bit string, can I just do this is just this? And then I don't need any of that nonsense. Yes. Can I get away with just making this bit string? Oh, yes, I think I can. So I think I made this way more complicated than it needed to be. So then up here, I can just say this is bit string. And I probably don't need send and sync here because this doesn't pass these to anything. And then this becomes compute score, spell, and no. Well, I do need the annoying vector business. Okay, let's just make this bool for now. It's not going to be pretty, but it will get the job done. And then, I read about that. No. Yes. No. Maybe I'm going to need to. This is going to have to be. Yeah, okay. That'll make that happier. So then I think we can make mutate work if we just put this in here. Boom, boom. Or not. Oh, it's probably got to be a reference. So this is going to have to be a reference. And that's going to have to be a reference because we don't want to give ownership away. Good. And then this is going to need to take if, and that all compiles, except it's saying that mutate doesn't use compute score. And that, oh, that's because it still says if. Compute score. Boom. Awesome. So now, fingers crossed, that will still work. Okay. And that looks like HIF scoring because we're up well above 128. And if I change this to count ones and count ones, the fact that I have this in two places is a bad sign. That could be, again, an argument for just adding it to the population when you construct the population. And that gives us 128. Okay, so that did a thing. We made a small improvement in the world. Not a big improvement in the world, but a little improvement. And there's still some grossness, but I did spend like an hour and a half explaining what was going on. So the faculty members, we like to hear ourselves talk, I'm afraid. So let's see. Here I could presumably do something as simple as let scorer be count count ones, and then I could put scorer here and here, and then I would only have to change it in one place, right? So that's going to be count ones, yeah. And then if I change this to be HIF, then it will do HIF stuff. Okay, so that's cool. That's a slight improvement. So now I only have to specify this once. It gets passed through everywhere, and gets passed through as arguments to these guys. I think there could be a place where the fact that I had to do this will maybe get me in trouble, but maybe not. I don't know. I guess if it doesn't, maybe I don't need to worry about it. Oh, yeah. If it doesn't, I guess I don't care. And I really prefer to have the functions take a slice if possible, because it makes them more flexible. So this is actually a good thing that this is a slice here, arguably. So, okay, well, if that worked, we'll have to at some point probably talk about the place where it didn't work and how I figured that out, but I'm not going to deal with that now. Okay, I'm going to commit. We got 3 minutes, and I should probably go do other things with my life. So what changed here? We introduced the score, and then this was all about adding compute score to these operators. I wonder if maybe I should have a trait that is a scorer, and then I can implement that trait in different ways. I don't know. I'm going to think about that, but not right now. So I'm going to commit this. So parameterize next generation and recombination ops with scorer. This adds a compute score argument to population bit string next generation, and the 2-point XO and mutate recombination operators. So we don't have specific scoring cooked into these functions. Doodly-doo, ba-ba-da-ba-da. And then here we just modify main to pass in scoring function. updates main to pass in a scoring function to next generation. Boom. Ba-da-ba-ba-ba. Okay, I think that is fine and dandy, and I'm going to call that a quits for the night. Thank you all for coming. It was awesome seeing a lot of people here. Appreciate it, and I think we'll, if this seems reasonable, we will continue doing this on Wednesday nights, and see if we can make progress on this, probably without having quite so much like just talking at the beginning. Saturday morning from 10 to noon Central Daylight Time, I'll be back working on the web app, ice-repos, using Rust and U. And Wednesday afternoon from 2 to 4, I will be working on a lab project for a course using Rust in our systems course, and try to do some new labs there that would use Rust in interesting ways. So, plenty of opportunities to watch more fun and excitement. Thank you for being here, and I will talk to everybody later. I hope you have a wonderful evening, morning, middle afternoon, whatever's happening in your world. And I look forward to seeing you again. Thanks a lot. We'll talk to you later. Bye.